Pleasure to be at this meeting, and I've thoroughly enjoyed the two talks so far. I'm looking forward to the rest of the talks, so thanks for inviting me. So I'm going to talk today about data assimilation, which is a little kind of different from the other sorts of inverse problems that we've heard about so far. And at the risk of insulting those in the audience who probably know far more about it than me, I'll start this talk with a bit of an introduction to data assimilation and how it is kind of implemented. And then towards the end of the talk, I want to talk about the work that I've done with the Met Office on modifying the way that they do a data assimilation to capture finer resolution in the data that they're interested in. And this is joint work with quite a big team. So in particular, Chiara Piccolo and Mike Cullen from the Met Office, who implemented a lot of the kind of techniques that I'm going to describe. And then various PhDs and postdocs from Bath and beyond who've also been very involved with the project. So what is data assimilation? Well, essentially what it is an optimal way of taking a model of some complex system, which comes with a ton of uncertainty, together with data from limited measurements of that same system, also which comes along with a ton of uncertainty. And the idea of data assimilation is that by combining a dodgy model with equally dodgy data, you can get an estimate for the underlying solution, which is hopefully more accurate than the data and more accurate from the model. So that's the plan. And basically, data assimilation does a pretty good job of achieving this result. So here is the basic idea. We have some system that we're trying to understand, and most of the systems that I shall be interested in this talk will be meteorological, and we have some true state of that system. So the atmosphere, as represented in a typical weather forecasting code, such as the unified model of the Met Office, has about 1 billion degrees of freedom. So XT is a very high dimensional object and can be even higher dimensional if we're looking at climate data as well. We then have some estimate of that system, some predicted state XB, and very often that predicted state will come from some previous calculation, and encoded within that predicted state are the laws of physics that we know are governing the underlying true state. So we want anything that we produce from our inverse problem to obey the laws of physics, and the predicted state is there to make sure that we do. We then take a series of observations of the true state, and usually these observations will be fairly limited. They may well be projections of the true state onto a much lower dimensional set. For example, they might be some sort of measurement along a line by a satellite averaging out, say, the temperature of the atmosphere across a line from the Earth's surface up to the satellite. And that, of course, not only will be a projection and therefore losing information, but that data will have errors in it as well. So what we're trying to do in data assimilation is to get a good estimate for the true state of the system, given this predicted state with errors and the observations also which have errors. So to give you some kind of idea of the scope of this problem, the data that we're typically measuring, particularly in atmospheric reconstructions in meteorology, is often extremely incomplete. It's often very multi-scaled. So meteorology has many scales, from the whole Earth down to the small length scales associated with turbulence. And the different data that you measure may have very different types of reliability. So just to give an example, the weather forecast for D-Day involved literally postmistresses looking out of their window in the west coast of Ireland and saying, this is what the weather is here. And those measurements, although they had lots of errors associated with them, because they were further west than the German observations, actually gave a much more accurate weather forecast at the end of the day. So in weather prediction, as I said, the atmospheric state typically has about 1 billion degrees of freedom, but the amount of data that you have to estimate that over a typical forecasting window, which is about 6 hours, is very much smaller. So you're lucky if you get 1 million measurements, and that will be a combination of data from satellites and ground states. So determining the true atmospheric state is a significantly underdetermined problem. And as I said, the data that we're using has all sorts of degrees of varying quality. And there is a snapshot of the various types of data we might expect, which varies from high quality but rather limited data coming from satellites to rather lower quality from manned stations on the ground, which, however, will give an extremely accurate measurement for what's going on the ground. So what we're trying to do in data assimilation then is to optimally estimate the system state xt, which is consistent both with the prediction and the physics underlying what we expect that state to do, and the data. And also, if data assimilation is really doing its job, we also want to get some measurement of the uncertainty so we can quantify the uncertainty in the state that we ultimately estimate. So I'll just start off with sort of a noddy problem. I apologize for this, but this is a problem I set my students as a way of getting their heads around what is going on in data assimilation. So let's assume that we want to estimate a single thing, which is the temperature of a room. And we measure the temperature of the room with a rather ancient thermometer. And that gives me a measurement, an observed temperature TO, which we know has an error AO, which may be quite large because the thermometer isn't very good. And then we estimate the temperature. So the thermometer says it's a nice warm day, but we see that the audience is wearing thick overcoats and is shivering. So we estimate from that the temperature might be rather lower. And there's our best estimate TB, which again has some sort of error EB. And then what data assimilation is doing is try to combine those two the measurement with the estimate to give a better estimate for the actual temperature. And the simplest way of doing this is to combine them linearly in the manner shown in the formula to give what's called the analysis, TA. I'm not quite sure where the word analysis comes from, but it's what the meteorologists always call the best estimate of the atmospheric state, which minimizes the overall error. And it's quite simple, assuming that TO and TB have uncorrelated errors, to then find the value of K, which minimizes that overall error. And if you do that, then the best estimate, the analysis estimate, turns out to be that thing in the blue box. So if EB is large and EO is small, then the analysis estimate is kind of dominated by the observed measurement. Whereas if EO is large and EB is small, then the analysis error is dominated by the estimated estimate. And it's easy to then calculate the overall estimated error, which is given by E squared in the purple box. And that is generally lower than either EO or EB taken individually. So that's essentially how data assimilation works, using in this case a quadratic cost function for the error. So there are basically two types of data assimilation. One is sequential and the other is kind of more historic, and I'll talk about historic in a minute. But the way sequential data assimilation works is that we have some sort of estimate of the state at some past time, xn minus 1. We then have some model of the system which produces our guess XB for the current state associated with some error. We then combine that with data, which again is some projection of the true state plus error. Then data assimilation produces this analysis XA, and then XA becomes our best state estimate at time XN. And then we can run forward the model to give us a forecast for, let's say, tomorrow's weather, which of course is what we're interested in if we're doing meteorology. And one aspect of meteorological data assimilation is, although you're working with huge problems with billions of degrees of freedom, and you've got a million data points, you can't afford to be too fussy in the way you do this, because you have to produce your forecast essentially in real time. So meteorological data assimilation tends to be a rather pragmatic mix between optimal theory and what you can achieve quickly so that you can get a real-time weather forecast. So that's basically the way that sequential data assimilation works. And this is kind of the basic idea behind it. So we have our estimate XB of the current state, which is the true state plus noise. So the purple kind of region represents the errors associated with the background estimate. Our data, similarly, is some projection of the true state plus noise. So again, we get this kind of ellipse associated with the errors of the data. And then we try to find some estimate XA, which is kind of somewhere between Y and XB, which minimizes the combined error between the two. And then XA is used to produce the forecast for the atmospheric state, typically for a typical forecast, which is 5 days or so in the future. Okay, so that's the basic problem. And as I said, it's a huge problem. We've got varying types of data on various different scales. And in meteorology, we have to do our calculations extremely quickly. So we have to make certain assumptions in order to get anywhere at all. And typical assumptions that are made are firstly that the errors themselves are Gaussian. Both the background error and the data error are unbiased Gaussian variables. And I should say that whereas the data error probably is an unbiased Gaussian variable, I do not believe the background error generally is as simple as that, because there's so many numerical issues that go in, which make it a bit systematic. But anyway, that is what you have to assume to make some sort of progress. Secondly, you assume that the data and the prediction errors are uncorrelated, which is sort of reasonable because the data error typically is associated with measurements of the atmospheric state, and the prediction error is associated with errors in the way you've constructed your model and constructed your numerical solution. And the third thing we tend to assume is that the projection operator is a linear one. And again, that's reasonable if we're kind of either averaging the data along some sort of path to get an average temperature, say, from the surface of the Earth to the atmosphere's top, or is simply sampling just one value of a large data set. So these are our general assumptions which are made in order to make progress. And then, having made those assumptions, we sharpen them up a bit. So we assume that the data error, I say, is Gaussian with some covariance R, which we will assume is known because R depends upon the way that we make our measurements, and therefore we've got a reasonably good idea about how accurate those are going to be. Similarly, we assume that the background prediction error is Gaussian with covariance B. B is something we tend not to know so well, and it may be too big to even store. And I'll come back to the importance of how we estimate B later on in the talk and show how that can lead to errors if not done carefully. And then data assimilation is essentially Bayesian. We try to get a maximum likelihood estimate of the data given the truth, which is given by M in the box there. And if we make all the various assumptions of Gaussian errors, then this maximum likelihood estimate is e to the minus j of x. And j is then a quadratic function, which is a linear combination of the error associated with the guess xb plus the error associated with the measurements of the data. So that is our j. And this conference is called Inverse Problems and Optimization, and data assimilation in this way naturally kind of fits into this, because we're trying to solve the inverse problem of estimating the atmospheric state by the analysis XA, and typically it's done as an optimization problem, so that we're trying to maximize the likelihood of the data, which corresponds to minimizing this function j. So stated this way, the inverse problem of estimating the atmospheric state becomes simply, well, simply isn't quite the word, but an optimization problem of finding the minimum value of j. Okay, so how do we do this? Well, if everything in sight is linear, and as stated, and we know what B is and we know what R is, then this problem is relatively straightforward to solve. The problem I did earlier on with the people shivering in the cold room was essentially exactly this, but in a kind of very simplified form. And the solution is obtained by the good old-fashioned Kalman filter. So I'm a great believer in the Kalman filter, and I think all applied mathematicians should learn about the Kalman filter alongside the conjugate gradient method and FFT. So I make sure my undergraduates know this. So this problem is quite well known, and if R and B are known, then the best estimate for the atmospheric state XA is given by the background state plus the Kalman gain matrix K acting on the data, where the Kalman gain matrix K is computable. I would say easily computable, but it isn't easily computable given the very large size of the problem that we are working with, and you know, where B here is a billion by a billion matrix, but in principle it is computable. And the great thing about the Kalman filter is that alongside giving us the atmospheric state estimate, it also gives us a very good estimate for the covariance of the error. And so we can quantify the uncertainty of our measurement relatively easily. And there's Kalman, who I believe originally developed the Kalman filter as a way of tracking aeroplanes and satellites using radar. And it continually updates the forecast and its error given the incoming data. Okay, so basically job done in a sense, except not. The two main problems with the Kalman filter for meteorological work are firstly that the sheer size of the problem makes it actually rather difficult to implement. And secondly, we don't really know what B is. So we can address the latter problem by using a kind of souped up version of the Kalman filter, which is the Ensemble Kalman filter. And this is actually very widely used as a method of data assimilation. It's certainly used by ECMWF in Reading, which is one of the top places in the world for meteorological data assimilation. And roughly in a nutshell, the idea behind the Ensemble Kalman filter is to use a Monte Carlo method where you take an ensemble of forecasts. So you have some understanding of the weather, let's say yesterday, and we take an ensemble of initial conditions based on our understanding of the weather yesterday and the error associated with that. And then we evolve each of those initial conditions forward in time to get a wide variety of background estimates. And then we take the sample mean and the sample covariance of those background estimates to give us our estimate of the covariance matrix B. So that's the Ensemble Kalman filter, and it's really coming into its own with modern parallel computers, where you can run a whole ton of ensembles very quickly. And in the sort of time I've been working on data assimilation, the number of ensembles that you can run has gone from in the tens to the tens of thousands. So it's really coming into its own. The alternative way of doing data assimilation is, rather than using the kind of Kalman filter method, is to directly go into the optimization problem and minimize the functional directly, the J function. And to do that, you use some sort of optimization method. And again, you can't afford to be anything very fancy in meteorological work, so you have to use fairly straightforward optimization methods which are quick to implement. And the preferred method is usually to assume that the analysis and the background are close, so that you've made a reasonably good forecast, and then you can approximate the function close to the background using some sort of quadratic function, and then use sequential quadratic optimization in order to get the value of J. And this is some sort of iterative process. It's quick and gives you an answer. It doesn't deal with particularly fancy meteorology, but it does get you there reasonably close quickly, which is essentially what you need. So that method has been implemented since 1999 in the Met Office. It's called 3D Var. And if you look at the kind of table that the Met Office has of the errors in their forecast over many years, you see a jump in the accuracy of the forecast when 3D Var was introduced. So it has made a difference. Although, as I said, the Ensemble Kalman filter is now essentially replacing it in many places because of the ease by which you can make ensemble forecasts. Now, 3D Var itself is not the complete method of choice amongst these optimization methods. And generally what is preferred is what is called the 4D Var method. So 4D Var takes data over 3 dimensions and also data over a series of time intervals within the 6-hour window, which is generally used to produce a weather forecast. In other words, you take data over 6 hours in order to estimate the atmospheric state, and then you use that estimate to produce your forecast. So essentially what you do in 4D Var is you take the background at some time and you evolve that forward 6 hours, and then you compare the background with the observations, and you take your analysis to be close to your background, and again you evolve that forward over the 6 hours and you compare it with the observations, and you produce a combined error J, which is a combination of the observation errors between the analysis and the data and the background error between the initial analysis and the background. Okay, and this is the what you then get. So in the box at the top, we see the background J function that you get in 4D Var, where you have on the left the error between the initial x0 and xb, and then on the right the error of between the measurements and the data over the n time periods that you have within your assimilation window. Now, if H is linear, the 3D Var problem is essentially a linear problem to solve, but the 4D Var problem is actually a very strongly non-linear problem. And the reason it's non-linear is that if I know what the weather is at time I and look forward to time I plus 1, then the operator on that is solving the extended Navier-Stokes equations, and therefore it is extremely non-linear operator. So the problem you have to solve to do this optimization is both the well, you basically have to minimize the function j, but subject to the strong model constraint that xi plus 1 is mi xi, where m is this highly non-linear function associated with the weather forecasting model that you're using, which in the Met Office is the unified model. So that makes 4D Var quite hard to use. And the way you typically do it is you calculate an adjoint matrix. So you essentially, by using back propagation, very much in the way machine learning works. And that gives you a series of adjoint problems, which you combine with the forward problem to give you a kind of a large system, which you then solve using a typical optimization method. One of the issues with the 4D Var as stated is that you assume a perfect model linking your xi state with your xi plus 1 state. And of course, the model isn't perfect and assumes you have to build in error as well. And putting that in gives you a thing called the weak constraint method, which is an extension of the 4D Var method. So anyway, that is currently what you're seeing is the 4D Var algorithm, which is, to all intents and purposes, the method of choice amongst the Met Office for current weather forecasting. And it's a nice stable method and reasonably hard to break, although you can break it if you put in quite severe type of weather moving through your system, such as acute storm fronts. So 4D Var and its derivatives has quite a lot of very good uses. Obviously, I've talked about it in weather forecasting, but it's also very useful if you've got a lot of historical data. And so it's used, for example, to look at models of flooding and tsunami. It's closely related, as I said, to machine learning, where you typically have a lot of historical data, can be used in climate modeling and in various other types of problem where you have historical data and you're not trying to do things in real time. Okay, so that kind of gives what I hope is a bit of a summary of data assimilation as it is currently implemented. But I want to talk a bit about some of the issues in using it. And one of the biggest issues is getting good estimates of the covariance matrices R and B. Now, the covariance matrix R, that's the data covariance matrix, isn't too hard to estimate. As I say, we know what our measurement state places are. We know what the sort of typical errors associated with them are. But B is much, much harder to estimate. This is the covariance matrix for the errors associated with our forecast. And we've got to get B right. Firstly, we want to make sure that our estimates of the atmospheric state get the underlying physics correct. Secondly, and this is very important, we want to make sure that we do not get spurious correlations between the various different parameters. So we don't assume two things are related when they're not. And I'm going to get on to why that's important in a minute. And thirdly, from a numerical point of view, you want to make sure that your systems are well conditioned. So B is a very large matrix, is so large it's difficult to store, difficult to update. And whereas if you have relatively small systems, you can generally get a good estimate from some sort of Fokker-Planck method. In general, B is rather hard to estimate. Even sort of the Ensemble Kalman filter methods that I was describing, you'd need to take a vast number of ensembles to get really good estimates for B. So what do? Well, what the Met Office does and other meteorological centres is try to get an understanding of the errors that you might make through a series of what are called control variable transformations. So what a control variable transformation does is to kind of try to produce what they call more natural physical variables, which have uncorrelated errors, so that the covariance matrix is block diagonal or even the identity. And that makes it much easier to work with and much easier to estimate the terms and gives better conditioning. So you try to build up some sort of transformation between your natural physical variables and the actual physical variables through a series of multiplications by transformation matrices. And that's then how you build up your covariance through then knowing what those are. So typically what's used in the Met Office is a first of all transformation which separates physical parameters, which we expect to be only loosely correlated, so that temperature, wind are loosely correlated, and balance and unbalanced. Basically, balanced meteorology is a slowly varying meteorology where you balance the pressure gradient with the Coriolis terms, and unbalanced is what you get when you move away from that. A second transformation projects the vertical behavior onto certain orthogonal modes. The atmosphere is very, very stratified, and therefore different bits of the atmosphere tend not to be too correlated with other bits vertically. And then thirdly, you try to reduce horizontal correlations by projecting onto spherical harmonics. So that's what's used, and it does work to a large extent, but errors still arise when you try this method due to lack of resolution of physical features, which leads to spurious correlations. And this observation was made by Mike Cullen, and that he then kind of brought this to my attention, and we then had a collaboration, which led to what I'm just going to talk about for the remainder of this talk. So Mike Cullen at the time was in charge of the data assimilation group of the Met Office. He's since sort of semi-retired, although he's still very active in what he's doing. Okay, so this is the problem that they were particularly interested in, and that is what is called an inversion layer. So here's an example of an inversion layer, and this is quite a common meteorological event. And what happens in an inversion layer is where you get cooler air trapped underneath warmer air. So in this picture, the Earth is cold, the atmosphere above it is warmer, and the kind of pollution that's coming from the factory gets trapped underneath the warm layer and forms a kind of mist and foggy area underneath. And this inversion layer, where cold air is trapped underneath hot air, is relatively stable and causes a large amount of problems with fog and pollution. And the reason this is a difficulty when it comes to data assimilation is that any measurements above the inversion layer tend to be uncorrelated with measurements below the inversion layer. But because the inversion layer is generally very thin, the kind of grids that are typically used in the vertical direction tend to smear it out, and they tend to then lead to data points above and below the inversion layer coming into the same grid cell, and therefore becoming spuriously correlated when you look at the kind of matrices, that the covariance matrices that are developed to do the data assimilation. And the poor resolution of the inversion layer can also lead to inaccurate predictions of fog and ice. And for us human beings, this is very important, because if you get a lot of fog, it means aeroplanes can't fly. And if you predict that incorrectly, then airports can lose vast amounts of money, or at least they would if they were flying planes. Of course, they're not at the moment. And the other thing is that ice, we need to predict ice very accurately if we are going to know whether to grip the roads or not. And if that is an error due to the way we're doing our data assimilation, that can be very costly, both in terms of lives and in terms of damage. Okay, so there are various solutions to this. The simplest solution, if you want to get your inversion layers correctly resolved, is to include the global resolution and include the number of data points. But this is very, very expensive. So to get better global resolution, if you want to halve your mesh size, that's typically going to increase the computational cost by a factor of probably about 100, because there's so much going on. So you don't want to increase your resolution without a potential increase in computer power. And if you do increase your resolution, you still need to increase your number of data points, and it's quite hard to suddenly put up twice as many satellites as you had before. So that's not really a practical solution, at least in the short term, although obviously as the Met Office and other weather centres get better and better computers, so the resolution can increase. But the typical resolution we have at the moment is sort of around about 1 to 1.5 kilometres, which is still quite coarse for an inversion layer. The second solution is to change your computational mesh locally when you're doing your data assimilation, so to better resolve the features associated with the inversion layer. And this is both cheap and effective, and this was what the team of us actually ended up implementing to improve the accuracy of the data assimilation methods that the Met Office were using. So what that amounts to in terms of kind of the data assimilation procedure is to introduce an additional transformation matrix we'll call UA, which is to do with adapting the mesh locally to resolve the location of the inversion layer. This is the basis of the algorithm that Mike Kalman, Chiara Piccolo, and I then developed to improve that. So how do you do that? Well, as I said, the atmosphere is strongly stratified, and in an inversion layer, everything is going on in the vertical direction. Not much is going on in the horizontal direction. So we developed a procedure where we adapted the mesh purely in the vertical direction, Z. So the idea is that you have what we call a computational variable xi, which relates to the underlying height variable, and it relates to it through the equation mz dz dxi is 1, where m is a monitor function. And what that monitor function, the way that works is that you make it large if you want, if something exciting is going on and you want your mesh to be compressed, and you make it order 1 if you don't really care what's going on. So that's the kind of idea. How do you choose your monitor function? Well, on the right, we have a graph where Z is the vertical coordinate, and to the horizontal coordinate is the temperature, theta. And you can see in the solid line a typical inversion layer, whereas you go up in height, so the temperature suddenly jumps. And so we can characterize an inversion layer pretty well by looking at the gradient of the temperature with respect to Z. And then you have to kind of normalize that a bit. And a typical monitor function we would use is then the square root of 1 plus c squared d theta dz squared, which is basically the meteorological variable called the potential vorticity. So what we do is adjust the mesh to allow for a much finer mesh when computationally we find there is high potential vorticity. So let's show you how that works. So on top left, we have a picture of the atmosphere, where the vertical component here is height, and the horizontal component is basically longitude, and this is at a particular latitude, which is essentially the UK's latitude. On the right, we can see the graph of the inversion layer, and you can sort of see where the inversion layer is in terms of the colors, top left, where we have colored in the graph so that red is associated with regions of high potential vorticity, and blue is associated with regions of low potential vorticity. And then the vertical mesh that is calculated using the method I described with the potential vorticity monitor is shown below, and you can see that the mesh is bunched up. In fact, this is the mesh in the location of this thing here, where the mesh lines are now bunched up close to where the potential vorticity is high, and we have the strong inversion layer. Now, the reason that this is very effective in terms of data assimilation is that if I have a point here below the inversion layer and the point here above, then we've now got lots of mesh lines between the two, and so these now become widely separated points in the covariance matrix, and therefore the spurious correlation is completely removed by this method. Okay, so seems to have missed some reason it's not showing the next slide. I apologize for that. I think I know what's happened there. When you actually apply this method to actual data, we find that the errors in the calculation obtained by removing this spurious correlation are significantly reduced. And one error in particular that was significantly reduced was the estimate of the temperature at 2 meters. So that's kind of human height. And this procedure actually ended up halving the error at 2 meters. And that was an extremely significant reduction in the error and led to a much better forecast as a result. And one thing that it did forecast better, because you've got better temperature resolution at 2 meters, was you have much better resolution of understanding of whether it's likely to be icy or not. And that could then be fed into a separate piece of software that the Met Office developed called Open Road, which advises councils on road gritting over Christmas. So
just a couple of minutes left, Chris.
Yeah, I'm nearly there. So basically, the method worked well enough to give councils much better advice on whether they should grit their roads or not. So that's adaptivity in 1D. Just to say, we are now extending it to a fully three-dimensional implementation, and the implementation uses adaptive methods based around optimal transport, and myself and some of my PhDs and postdocs, we've now managed to kind of extend this to fully three-dimensional, and that is kind of work that's sort of ongoing between us and the Met Office. And I should say that the one-dimensional adaptivity and the reduction in errors were sufficiently good to be adopted operationally by the Met Office. So they are using this every 6 hours to forecast the weather. The three-dimensional methods, which are showing great promise, are under development and may be implemented operationally in about 10 years when the Met Office have finished testing them. It's a slow old process getting things operational with the Met Office, but things are looking promising. So I'll skip through the OT side and just say there is one of the meshes that we've now constructed around an inversion layer, and that's a cross section through a fully three-dimensional mesh. So to conclude, data assimilation is an optimal way of merging models with uncertainty with limited data, also with an uncertainty. And it can be used for many things. It's primarily used for forecasting, but it can be used for tuning models, validating them, and quantifying uncertainty in them, and also for upscaling and downscaling. And it's widely used in meteorology and increasingly used in other ways. And in the particular case of trying to predict temperatures close to the Earth, it can be significantly improved by using adaptivity and optimal transport methods. So thank you very much, and I'm happy to answer questions.